A lunar space elevator is not science fiction, but a serious engineering proposal. For decades, the dream of a space elevator belonged to Earth, a cable stretching into the heavens to make orbit cheap and accessible. That dream has always crashed against our planet's brutal gravity and thick atmosphere. But what if we built it on the moon instead? This video delivers a definitive feasibility analysis, giving you a clear verdict on whether this megastructure could become the backbone of lunar industry. We will dissect the astonishing physics that makes it possible, confront the one material that could bring it all down, and calculate the economic logic that might justify its staggering cost. The stakes are the future of a permanent lunar economy and our gateway to the wider solar system. So, is the moon the perfect construction site for humanity's first space elevator? Or is this an elegant trap for our ambitions? The classic vision is a slender ribbon of carbon nanotubes anchored at the equator and stretching upward for over 22,000 miles. At that incredible altitude, the cable's center of mass would reside in geostationary orbit, allowing it to hover over a single point on Earth as our planet rotates. It is an elegant solution in theory, a celestial bridge that could carry cargo and people into space for a fraction of today's cost. Yet for all its promise, this Earth elevator has remained trapped on the drawing board. The challenges are immense. Our planet's strong gravity demands a material with nearly impossible tensile strength, something far stronger than even the finest steel. Our thick atmosphere creates constant drag and exposes the structure to punishing weather. And perhaps most daunting of all, low Earth orbit is a crowded shooting gallery of space debris, each tiny fragment a potential bullet that could sever the entire cable. This perfect storm of obstacles has kept the idea firmly in the realm of future speculation. But shift your gaze 250,000 miles away, and the entire equation changes. The moon presents a completely different set of rules. It has no atmosphere to create drag or weather. Its gravity is only 1/6 of Earth's, dramatically reducing the strain on any supporting structure. And its slower rotation, while creating a different orbital puzzle, simplifies the engineering in key ways. This stark contrast is the foundation of a compelling new argument. What if we have been dreaming of the wrong world all along? The lunar surface, barren and quiet, might just be the ideal construction site for humanity's first true space elevator, turning a century-old dream into a tangible blueprint for the future. The true power of a lunar elevator lies in its economics, a simple equation that could unlock the solar system. Right now, getting anything off the moon requires a rocket. Every kilogram of water ice, every piece of processed metal, every scientific instrument destined for a lunar orbital station needs its own explosive launch from the surface. Rockets are complex. They require fuel that itself must be transported from Earth at astronomical cost, and each launch is a high-stakes event with limited cargo space. This creates a punishing cycle where building anything substantial in lunar orbit becomes prohibitively expensive, stifling ambition before it even leaves the ground. A space elevator shatters that cycle. Think of it not as a tower but as a celestial railway. Once built, it operates on electricity, likely beamed from solar power stations on the surface. Climbers, essentially robotic freight cars, would ascend the ribbon at a steady, controlled pace. They would not fight gravity with brute force, but simply climb out of the moon's shallow gravity well. The cost per kilogram to reach orbit could plummet by a factor of 100 or more, transforming lunar resources from a theoretical asset into a practical, flowing commodity. This changes everything. Suddenly, the water ice locked in permanently shadowed craters at the South Pole can be mined, loaded onto a climber and shipped to a depot at a Lagrange point, where it is split into hydrogen and oxygen, the fundamental components of rocket fuel. A deep space mission to Mars no longer needs to haul all its propellant from Earth, a massive weight penalty. It can refuel at a lunar way station, stocked by the steady, cheap supply line of the elevator. Lunar bases themselves become more sustainable, as bulk materials for radiation shielding or construction can be lifted from the Moon's own regolith, instead of being painstakingly shipped from Earth one rocket at a time. The elevator is not just a transportation method, it is the foundational piece of economic infrastructure, the turnpike that makes a permanent, growing lunar economy not just possible but inevitable. It shifts the financial logic from short-term, expensive campaigns to a long-term investment in permanent access. The initial cost to build it would be enormous, a multi-decade project requiring international cooperation. But once operational, every subsequent mission, every kilogram of cargo becomes cheaper. It pays for itself not in cash, but in the unlocked potential of the Moon itself, creating a gateway where the greatest cost of doing business in deep space, the launch from a planetary surface, is reduced to a minor logistical footnote. This is the compelling case, a vision where the Moon stops being a distant destination and becomes our most important industrial port. This elegant solution hinges on a subtle trick of celestial physics. To understand why a lunar elevator is even possible, we must first abandon the classic Earth-based model. Our planet's elevator relies on reaching geostationary orbit, a specific altitude where a satellite's orbital period matches Earth's 24-hour rotation, allowing it to hover over one spot. The Moon rotates much slower, completing one turn every 28 days. A satellite in low lunar orbit whips around the surface in just a couple of hours. This mismatch means there is no equivalent lunar geostationary orbit for a traditional cable to reach. So where do we anchor it? The answer lies not in orbit around the Moon, but in the gravitational balance points between the Moon and Earth. These are called Lagrange points. Picture the complex dance of gravity between two massive bodies like Earth and the Moon. At 5 specific locations in this system, the gravitational pulls and centrifugal forces perfectly cancel each other out. An object placed at one of these points will hold its position relative to the two bodies with minimal effort. For a lunar space elevator, 2 of these points are crucial. L1, the first Lagrange point, sits on a direct line between Earth and the Moon, about 35,000 miles from the lunar surface, much closer to the Moon than to Earth. Here, the tug of Earth's gravity and the Moon's gravity are balanced. L2, the second Lagrange point, sits on the far side of the Moon, also in that line, but in the opposite direction, away from Earth. A lunar space elevator would not be a free-standing tower, but a tether, a super-strong cable anchored at one end on the Moon's surface. The other end would extend out through space, not to a counterweight in orbit, but all the way to one of these Lagrange points. Imagine a cable anchored at the Moon's equator. It could extend upward through L1, pointing back toward our blue planet. Alternatively, a cable could extend outward from the far side through L2, pointing away into deep space. At the Lagrange point, the cable's end is essentially parked in a gravitationally stable parking spot. The entire structure is static, held in place by the fundamental forces of the solar system. Payloads would not rocket into space. Instead, robotic climbers, like electric trains on a vertical track, would ascend this fixed cable. They would use solar power or beamed energy to slowly but steadily climb out of the Moon's weak gravity well, delivering their cargo directly to the strategic gateway of a Lagrange point. This is the core mechanical principle, a bridge built not on rock and steel, but on the invisible geometry of gravity itself. The elegance of this gravitational bridge, however, meets its ultimate test in a single, tangible component, the cable itself. This is the heart of the machine, and its demands push the very limits of material science. To span the vast distance from the lunar surface to a Lagrange point, the tether must possess an extraordinary combination of qualities. It must be incredibly strong for its weight, a property engineers call a high tensile strength to density ratio. It must endure the relentless bombardment of micrometeoroids and cosmic radiation without degrading. And above all, it must be manufacturable on a scale we have never before attempted, not as laboratory curiosities, but as a continuous, flawless ribbon tens of thousands of miles long. For decades, the dream material has been carbon nanotubes. These are microscopic cylinders of carbon atoms arranged in a hexagonal lattice, and in theory, they are hundreds of times stronger than steel while being astonishingly light. Their flat cousin, graphene, a single layer of carbon atoms, shares this legendary strength. If we could weave these nanomaterials into a macro-scale cable, the problem would be solved. But here we confront the harsh reality of the laboratory. We can produce carbon nanotubes, but we cannot yet assemble them into long, continuous fibers without introducing microscopic defects. A single weak point in a structure under such immense tension could be catastrophic. The manufacturing techniques to create a perfect, macroscopic ribbon from these nanomaterials simply do not exist today. It is like discovering a recipe for a miracle alloy, but only being able to produce a few specks of dust at a time, when what you need is to forge the cables for a planetary suspension bridge. This is the biggest hurdle, a chasm between theoretical promise and practical engineering. Yet, for the lunar elevator, there is a crucial note of optimism. The material requirements, while still staggering, are far less severe than for an Earth-based version. The Moon's weaker gravity means the cable does not have to support as much of its own immense weight. This opens the door to considering other advanced materials, like ultra-high-strength polymers or next-generation composites, which might be feasible to manufacture in the coming decades. The quest is not for a perfect material from science fiction, but for the best possible material from the near future, one strong enough to turn a lunar dream into a blueprint. The search for this ribbon is the quiet, decades-long race happening in laboratories around the world, where the success of our largest celestial ambitions depends on the smallest of atomic bonds. The choice of where to attach this celestial cable is not arbitrary. It is a strategic decision with profound consequences for the entire system. We have two ends to secure, one on the lunar surface and the other out in the void at a Lagrange point. Each anchor point presents its own unique set of challenges and opportunities, defining the very nature of the elevator's operation. Let us start with the foundation, the lunar base. Anchoring the tether directly to the Moon's surface offers immense stability. The foundation would likely be a massive, heavily engineered station built into the bedrock, perhaps at the edge of a large equatorial crater for optimal alignment. This ground anchor must handle not just the constant pull of the cable, but also the stresses induced by the Moon's libration, its slight wobble as it orbits Earth. The advantage here is direct access. Climbers would begin their journey from a fixed, serviceable base where they can be loaded with lunar regolith, ice, or manufactured goods. The surface becomes a bustling spaceport, the starting point of the cosmic supply chain. The far end of the cable, however, floats in the emptiness of space. This is the counterweight anchor, and its engineering is more abstract but equally vital. It does not need to be a single, solid mass. One compelling proposal is to use a captured asteroid, nudged into position at the Lagrange point and tethered to the cable. Another is a spent spacecraft or a purpose-built station, acting as both a counterweight and an operational hub. The counterweight's job is to keep the cable taut, using centrifugal force from the Moon's slow rotation and the balanced gravity at the Lagrange point to maintain the structure's integrity. This is where the choice between Lagrange point 1 and Lagrange point 2 becomes critical. A cable to L1, which lies between Earth and the Moon, is shorter, roughly 35,000 miles long. This makes construction slightly less daunting and reduces the cable's total mass. However, L1 is a gravitationally busy area, a future highway for lunar traffic, which could pose navigation hazards. A cable to L2 on the far side of the Moon is longer, perhaps 50,000 miles or more, increasing the material challenge. Yet L2 offers a pristine, radio-quiet environment perfect for deep space observatories and an unobstructed launch point for missions directly into the solar system, away from Earth's gravitational influence. The beauty of this puzzle is that both options are valid. The differences in cable length and destination are matters of engineering trade-offs, not fundamental physics. We are not breaking any laws of nature, we are simply solving an extraordinarily complex logistics problem. Whether the anchor is a bustling base at Shackleton Crater or a silent, captured rock holding its position at a point of perfect balance, the principles remain sound. This is not science fiction, it is systems engineering on a cosmic scale. But the ribbon is only a road, it needs a vehicle. The climber is the workhorse of the lunar elevator, a robotic freight car tasked with the slow, steady ascent out of the Moon's gravity well. Unlike a rocket, it does not fight its way to space with explosive force. Instead, it simply grips the tether and climbs, like a train on a vertical track or an electric car driving up an impossibly long, thin mountain road. Its design is deceptively simple in concept, yet fiendishly complex in execution. At its core, the climber needs a reliable method of propulsion. The most likely solution is a system of motorized rollers or magnetic grips that latch onto the ribbon, pulling the vehicle upward without damaging the delicate cable. Powering this long journey presents its own puzzle. A climber making the several-day trip from the lunar surface to a Lagrange point cannot rely on batteries alone. They would be far too heavy. The leading candidates are solar power or beamed energy. Solar panels covering the climber's structure could harvest sunlight, but they would be useless during the long stretches of the climb in shadow. A more consistent solution might be to beam power to the climber, either from massive solar arrays on the lunar surface or from stations positioned along the cable itself, creating a kind of energy relay to keep the vehicle moving through the perpetual night of space. Speed is a deliberate trade-off. To minimize power requirements and mechanical stress, the climber would move slowly, perhaps at a steady pace of 100 miles per hour or less. At that rate, the journey to a Lagrange point would take over 2 weeks. This is not a passenger transport, it is a bulk cargo system, prioritizing immense reliability and low cost over speed. Every minute of that multi-day climb happens in one of the most hostile environments imaginable. The climber must be a fortress. It will swing from baking sunlight into the deep freeze of shadow, experiencing temperature swings of hundreds of degrees in minutes. Its electronics must be hardened against a relentless hail of cosmic radiation that would fry ordinary circuitry, and it must do all this while maintaining an absolute, fail-safe grip on the only thing connecting it to the Moon below. Redundancy is not a luxury, it is the entire design philosophy. Every critical system, from the gripping mechanisms to the guidance computers, would need multiple backups. The climber must be able to detect a problem, switch to a reserve system, and perhaps even perform repairs on itself, all while hanging from a thread 35,000 miles above the lunar surface. Safety systems would need to account for every conceivable failure, including the catastrophic possibility of a cable break. In such an event, the climber would need to instantly transform from a train car into a spacecraft, using small thrusters to maneuver itself into a stable orbit or execute a controlled landing. This vehicle is more than a machine. It is a testament to autonomous engineering, a silent, patient courier operating in a vacuum of silence and extremes, where every bolt, every wire, and every line of code must be perfect. Its successful journey, repeated thousands of times, is what transforms the elegant physics of the tether into a river of lunar resources flowing into the heavens. The moon's serene, airless silence is a profound deception. For a structure as delicate as a space elevator, this environment transforms from a blank canvas into a gauntlet of relentless, abrasive threats. Three silent adversaries stand ready to degrade the system: lunar dust, extreme temperature, and a constant rain of tiny projectiles. First, consider the dust or regolith. This is not like Earth dust. Lunar regolith is the product of billions of years of meteoroid impacts with no atmosphere or water to soften the edges. Each particle is a tiny, sharp, glass-like shard, electrostatically charged by the sun's radiation to cling to everything it touches. For a climber ascending the tether, this dust is a nightmare. It could infiltrate every moving part, the gripping mechanisms, the motorized rollers, the joint seals, acting as a powerful abrasive that grinds components to a halt. A single grain could compromise a vital electrical connection. Mitigating this requires a fortress-like approach. Climbers would likely be designed with sealed, pressurized compartments for critical electronics. Moving parts might use magnetic levitation instead of physical rollers to avoid contact wear. The tether itself could be coated with a slick, non-stick material to prevent dust accumulation, and active cleaning systems, perhaps using electrostatic brushes or gentle puffs of gas, would be essential maintenance during the climber's journey. Then there is the temperature, a cycle of brutal extremes. For 2 weeks, the lunar surface bakes under unfiltered sunlight, reaching temperatures hotter than boiling water. For the next 2 weeks, it plunges into a deep freeze colder than any place on Earth. A structure stretching from the surface into space will experience these wild swings along its entire length. Metals and composites expand and contract with temperature, and repeated over thousands of cycles. This thermal fatigue can create microscopic cracks, weakening the material over time. The cable and climber must be engineered not just to survive these swings, but to operate through them. This could involve using materials with a very low coefficient of thermal expansion, or designing the tether with a clever braided structure that allows for slight movement without compromising strength. Heating elements and radiators on the climber would actively manage its internal temperature, ensuring its sensitive machinery stays within a safe operational range, whether it is climbing through the inferno of lunar noon or the deep chill of the 2-week-long night. The most unpredictable threat, however, comes from above. The moon has no protective atmosphere, which means even the tiniest speck of space dust, a micrometeorite, strikes with the force of a bullet. These are not the dramatic asteroid impacts of movies, but a constant, high-velocity sandblasting from particles smaller than a grain of sand. While a single impact is unlikely to sever a robust, multi-stranded tether, the cumulative effect of millions of such hits over years could fray and weaken its surface. Furthermore, a larger impact, perhaps from a pebble-sized object, could potentially damage a critical section. Defense here involves both passive and active strategies. The tether could be wrapped in a sacrificial outer sheath, a layer designed to absorb these impacts and be periodically inspected or replaced. More actively, a network of telescopes could monitor the immediate vicinity of the elevator, tracking the orbits of larger debris fragments. If a dangerous object is predicted to pass too close, small thrusters on the counterweight or along the cable could make minute adjustments, gently moving the entire ribbon out of harm's way in a slow, deliberate dance to avoid a collision. These are not insurmountable barriers, but they are formidable design specifications. They demand materials and systems that are not only incredibly strong and light, but also dust-proof, thermally resilient, and self-healing to a degree. Meeting this challenge means building a machine that is less like a bridge and more like a living organism, one capable of enduring, adapting, and maintaining itself in the most unforgiving construction site humanity has ever known. Building this bridge would be the most complex engineering project in human history. The sheer scale defies comparison, a structure longer than the circumference of our planet, assembled in the silent, airless void. It cannot be built from the ground up like a skyscraper. Instead, it must be spun from the heavens down, a reverse spiderweb woven between the moon and a point of gravitational balance. This demands a meticulously choreographed sequence, likely unfolding over decades. The first act would not involve the tether at all, but robotic scouts. Autonomous landers would descend to potential anchor sites on the lunar equator, scouting for stable bedrock and conducting final surveys. Simultaneously, missions would be sent to the chosen Lagrange point, perhaps to position a captured asteroid or deploy the initial counterweight station. This phase is about establishing the two bookends of our cosmic bridge before we string the cable between them. The next challenge is the cable material itself. Manufacturing tens of thousands of miles of ultra-strong ribbon on Earth and launching it would be astronomically expensive and risky. The most logical solution is to make it in space. One visionary proposal involves using resources already present in the lunar environment. Automated processing plants on the moon could mine regolith, extract metals like aluminum and titanium, and feed them into orbital factories that spin the refined material into high-strength wire. An even more ambitious idea looks to the asteroids, those rocky bodies rich in metals, using robotic miners to harvest raw material and process it at the construction site. This in-situ resource utilization transforms the project from a supply chain nightmare into a closed-loop system, where the elevator helps build more of itself. With the anchor points ready and the material production underway, the delicate dance of deployment begins. The process might start at the counterweight in deep space. A spacecraft would begin slowly unreeling the initial, hair-thin tether, descending toward the moon while simultaneously using gentle thrusters to maintain position at the Lagrange point. This is an operation of incredible patience and precision, taking months as the filament grows longer. As the descending tip approaches the lunar surface, a waiting rover would capture it and secure it to the massive ground anchor. At that moment, the bridge is closed, but it is still just a single, vulnerable thread. The real work now strengthens it. Climber robots launched from Earth or built on the moon would begin their endless journeys. The first climber would ascend this initial strand, unreeling a second parallel cable alongside it. Subsequent climbers would weave additional strands, gradually braiding the single thread into a robust, multi-stranded ribbon capable of supporting real cargo. This bootstrapping phase could take years, a slow and steady crescendo from fragility to strength. This timeline reveals the true nature of the endeavor. A lunar space elevator is not a project for a single company or even one nation. It is a century-defining undertaking on the scale of the International Space Station, but far grander. It would require an unprecedented, sustained international partnership, binding together the scientific, economic, and political will of generations. Funding would need to be resilient, surviving economic cycles and changes in leadership with a shared, long-term vision. The construction would be a symphony of robotics, with human oversight from lunar orbit or Earth, managing fleets of autonomous builders in a coordinated ballet across 250,000 miles. The payoff would not be immediate, but its completion would mark a fundamental shift, the moment we stopped just visiting the moon and began integrating it into the economic sphere of human civilization. The elevator would stand not just as a tool, but as a monument to long-term thinking, a testament to what we can build when we look beyond the horizon of a single lifetime. The silent construction site of a lunar elevator would have no human workers. This is not a choice, but a physical necessity dictated by the vast, empty gulf between Earth and the moon. The communication delay, that frustrating lag in a video call, becomes an unbridgeable chasm for real-time control. A signal traveling at the speed of light takes about 2.5 seconds to make the round trip. 2.5 seconds might not sound like much, but for a robot delicately threading a new strand into a multi-braided cable, or for a climber detecting a micrometeoroid strike, it is an eternity. In an emergency, by the time an engineer on Earth sees a problem and sends a command, the situation could have already escalated beyond recovery. This fundamental law of physics makes full, advanced autonomy the only possible foreman for this project. The entire life cycle, from the first ground survey to decades of maintenance, must be entrusted to machines that can think, decide, and act for themselves. Consider the phases of work. Before a single meter of cable is deployed, robotic landers must prepare the anchor site. These would not be simple rovers. They would need to be heavy construction vehicles capable of using drills and grapplers to level terrain, excavate foundations, and emplace the massive anchoring hardware, all without a human hand on the controls. Following them, the cable deployment spacecraft itself is a robot of exquisite precision, tasked with unreeling a fragile thread across tens of thousands of miles of void, constantly adjusting its thrust to maintain perfect alignment. Even the climbers that will later strengthen the tether are, in their initial form, autonomous builders. Their programming must handle the immensely complex task of rendezvousing with a flimsy, moving cable in microgravity, latching on, and then performing a careful, synchronized dance of weaving and integration, all while managing their own power and thermal systems. This is not pre-scripted movement. This is adaptive robotics, where machines perceive their environment through a suite of sensors, cameras, and lasers, and make continuous micro-adjustments to complete their task. They are not just tools, they are independent craftsmen. The need for intelligence goes beyond construction into the realm of perpetual care. Once operational, the elevator demands constant vigilance. AI-driven inspection climbers, equipped with high-resolution scanners and sensitive strain gauges, would make regular journeys up and down the ribbon, looking for the telltale signs of wear: a frayed section from dust abrasion, a tiny pit from a micrometeoroid impact, or the beginnings of thermal fatigue. Upon finding a flaw, the system could not wait for a committee meeting back on Earth. An autonomous repair drone, perhaps stationed at a maintenance hub along the cable, would need to be dispatched immediately. This repair bot would have to assess the damage with its own artificial eyes, select the correct procedure from its memory, and then execute a delicate operation, perhaps applying a composite patch or splicing in a new segment with the steady precision of a surgeon. All of this happens in the quiet of space, with Earth as a distant advisor, not a direct controller. The AI systems managing this would need a level of robust decision-making we are only beginning to develop. They must understand priorities, triage simultaneous alerts, and even manage their own logistics, deciding when to return to a depot for more repair material or power. This transforms the elevator from a static structure into something almost organic, a self-aware system capable of healing its own wounds, ensuring its longevity not through brute strength alone, but through intelligent, autonomous care. The success of humanity's greatest bridge depends on the quiet, unseen competence of machines we have yet to fully build. The staggering scale of this project brings us to the most practical question of all: who writes the check? Technical feasibility is one thing, but economic feasibility is the gatekeeper that decides if blueprints ever become steel and carbon fiber. We must shift from physics to finance, from material science to market logic. The initial investment would be measured not in billions, but likely in hundreds of billions of dollars, a sum that demands a compelling return. So who would shoulder this cost, and what would convince them it is worth the risk? The funding models break down into three broad pathways, each with its own philosophy and pitfalls. The first is the traditional route: government space agencies. A consortium like NASA, the European Space Agency, and the China National Space Administration could pool resources, framing the elevator as a strategic, century-scale infrastructure project for all humanity, akin to building the interstate highway system or the International Space Station. This model offers stability, deep technical pockets, and a mandate that looks beyond pure profit to scientific discovery and geopolitical prestige. Yet it also moves at the speed of bureaucracy, subject to shifting political winds and public budgets that can evaporate with a change in administration. The second path is the private consortium, a coalition of corporations with skin in the game. Imagine a partnership led by entities like SpaceX, Blue Origin, and major aerospace contractors, perhaps joined by mining or energy giants. This model is driven by a clear business case and can move with disruptive speed, much like the development of reusable rockets. Their motivation is not prestige, but profit, and they would demand a rigorous plan for monetizing the elevator's operations from day one. The third and perhaps most realistic model is a public-private partnership. Here, governments provide the foundational investment, de-risking the initial, most uncertain phases of research, development, and anchor site establishment. Once the core technology is proven, private entities take over the financing, construction, and operation under a long-term lease or revenue-sharing agreement. This blends the long-term vision of public institutions with the efficiency and innovation of the private sector. But under any model, the business case must be ironclad. The elevator cannot be a monument, it must be a money-maker. Its value proposition rests on two powerful pillars. First, it enables lunar resource economics. The steady, cheap lift it provides makes mining the moon's water ice for rocket fuel, or harvesting rare isotopes like helium-3 for future fusion reactors financially viable for the first time. The elevator turns abstract resources into flowing revenue. Second, it serves as the ultimate transportation hub. By slashing the cost of leaving the moon, it transforms a lunar orbit depot, stocked with locally made fuel, into the most logical launch point for crewed missions to Mars and beyond. Every deep space mission that refuels there represents a customer, paying a toll to use the gateway the elevator built. The financial argument is not about a quick return, but about building the indispensable piece of infrastructure for the next era of spacefaring civilization. The entity that owns that bridge owns the toll booth to the solar system. But a project of this magnitude does not exist in a vacuum of pure engineering. Beyond the physics of materials and the mathematics of orbits lies a more complex human terrain, the legal and political landscape of outer space itself. The moment we begin pouring a foundation on the moon or anchoring a cable to its surface, we move from theoretical physics to international law. The framework for this endeavor was written in a different era, long before private companies or permanent lunar bases were a realistic consideration. The cornerstone is the 1967 Outer Space Treaty, a document signed at the height of the Cold War. Its principles are grand and visionary, declaring that space is the province of all mankind, not subject to national appropriation by claim of sovereignty. No nation can plant a flag on the moon and call it its own. The treaty also mandates that states bear international responsibility for national activities in space, whether conducted by government agencies or private companies, and requires that all activities be carried out for the benefit and in the interests of all countries. This creates a fascinating legal environment for a lunar elevator. A company or nation could build it, but they could not claim the territory underneath its anchor as sovereign soil. They would have the right to use the structure, but its operation would need to consider the broader interests of the international community. A later agreement, the 1979 Moon Agreement, goes further, proposing that the moon and its resources are the common heritage of humanity, and suggesting an international regime to govern resource exploitation. However, this treaty has not been ratified by any major spacefaring nation, leaving its principles in a state of diplomatic limbo. This legal ambiguity is the seed of potential conflict. Imagine the most valuable real estate on the Moon, like the rim of Shackleton crater at the South Pole, a site bathed in near-perpetual sunlight adjacent to permanently shadowed ice reserves. It is a perfect location for a solar-powered base and a potential elevator anchor. Under current law, no one can own it but who gets to use it first. If one nation or company establishes a permanent anchor facility there, have they effectively, if not legally, appropriated the most strategic location on the Moon? This is not science fiction, it is a near-future diplomatic crisis waiting to happen. The elevator itself, as a shared transportation corridor, would become a global utility of unprecedented importance. Its operations would need new frameworks, rules for traffic management, safety standards, liability for accidents, and protocols for emergency access. Would it be run by a multinational authority, like a celestial version of the International Civil Aviation Organization? Or would it be a private toll road regulated by a patchwork of national licenses? The need for clear, forward-looking governance is as critical as the need for a strong cable. Without it, the very project designed to unite humanity's reach into the solar system could become a source of terrestrial dispute. The success of the elevator depends not just on carbon nanotubes and autonomous robots, but on our ability to craft treaties and agreements with the same ingenuity we apply to engineering, building a legal architecture robust enough to support our celestial ambitions. Given the scale, a working lunar elevator is not a project for this decade or even the next. Its construction will unfold across generations, a slow and steady march of robotic pioneers. We can sketch a realistic, staged timeline by looking at the pace of other human megaprojects. The International Space Station, for instance, took over a decade of continuous assembly flights and international coordination just to become operational. A lunar elevator is an order of magnitude more complex, built in a far more hostile environment, and with no existing supply chain. With sustained, focused effort, an optimistic projection might see the first operational cargo climbers ascending a thin, initial tether by the 2050s or 2060s. This would require a global commitment to begin serious development within the next 10 years, treating it with the urgency and funding of a moon landing program. The conservative, perhaps more realistic estimate pushes a fully functional industrial-scale elevator into the latter half of this century, possibly the 2080s or beyond. This timeline is not dictated primarily by the technology. The fundamental physics is understood. The material science, while demanding, is progressing. The true bottleneck is the human element, the sustained political and economic will to see a century-defining project through from conception to completion. Such an endeavor must survive economic downturns, changes in government, and shifting public priorities across multiple decades. It requires a long-term vision that transcends electoral cycles and quarterly profit reports, a shared agreement that building this celestial bridge is a legacy worth leaving for the future, even if those who start it may not live to see its first cargo reach the Lagrange point. The story of the lunar elevator, therefore, is less about predicting a year on a calendar and more about measuring our collective ambition. It asks whether our civilization can look beyond immediate challenges and invest in an infrastructure that will unlock the solar system for our children's children. The clock is not counting down to a launch date, but ticking away on our willingness to begin. The dream of a celestial bridge is not exclusive to the Moon. As we look outward, similar concepts have been sketched for Mars and even for capturing small asteroids. Each offers a different vision, but placing them side by side reveals why the lunar elevator is not just possible, but the most pragmatic first step. Mars, with its own ambitions for human settlement, seems a natural candidate. Its gravity is about 38% of Earth's, stronger than the Moon's but still manageable. An elevator there could theoretically connect the surface to a moon like Phobos or to a station in Aerospace orbit. The engineering challenges, however, multiply with distance. Mars is on average 140 million miles away. Every tool, every robot, every kilogram of specialized material for construction would need to be launched from Earth on a months-long journey, with no possibility of timely rescue or resupply if something goes wrong. The communication delay balloons to 20 minutes each way, making real-time control impossible and demanding an even higher, untested level of machine autonomy. Furthermore, we have not yet landed humans on Mars, let alone established the permanent industrial base needed to support a construction project spanning decades. The Martian elevator is a compelling vision for a future century, but it is a second step, not a first. Asteroids present another fascinating model. Some proposals envision a space elevator that is not anchored to a planet at all, but is a rotating cable system between a captured asteroid and a smaller counterweight, creating artificial gravity for a habitat or a sling to fling payloads across the solar system. The lower gravity of a small asteroid makes the material strength requirement trivial compared to a planetary elevator. Yet this approach sidesteps the core economic driver, lifting valuable resources from a planetary surface to where they are needed. An asteroid elevator is more of a deep space processing station, useful but not solving the fundamental problem of accessing materials from a gravity well. This comparative analysis brings the Moon's advantages into sharp, undeniable focus. Its proximity is its greatest asset. A mere 3-day journey from Earth, it allows for relatively rapid resupply, hands-on human oversight from orbit if needed, and a manageable communication lag that makes complex robotics feasible. Its weaker gravity well is the shallowest of any substantial body in the inner solar system, making the climb easier and the material demands less extreme. Most critically, we are already going there. International plans for permanent lunar bases, led by NASA Artemis program and joined by other nations, are not speculation, they are active policy. This creates a ready-made customer base and construction zone. The first lunar elevator would not be built in isolation. It would be built to serve a growing colony that already needs to move massive amounts of regolith for habitats, water ice for life support, and manufactured goods for orbital depots. The Moon becomes the logical proving ground, the test bed where we learn to build and operate off-world infrastructure in a relatively forgiving environment before attempting it on distant, more hostile worlds. Choosing the Moon is not about dismissing the grandeur of Mars or the potential of asteroids. It is about recognizing the most strategic beachhead, the place where the physics, the economics, and the timeline of human exploration all converge to make a celestial bridge not just imaginable, but inevitable. The true legacy of a lunar elevator might not be the structure itself, but the cascade of innovation it would unleash. This megaproject would act as a powerful catalyst, forcing breakthroughs in fields that extend far beyond the lunar surface, spinning off technologies that reshape life on Earth and accelerate every other space ambition. The demand for a flawless, tens of thousands of miles long cable would push material science into a new era. Researchers would not just be making stronger fibers, they would be perfecting the art of manufacturing them in space, developing techniques for large-scale, zero-gravity fabrication of flawless composites. The processes invented to weave this cosmic ribbon could revolutionize industries back home, leading to new generations of ultra-light, ultra-strong materials for everything from earthquake-resistant bridges and fuel-efficient aircraft to next-generation medical implants and protective gear. The quest for the perfect tether is a quest for a new class of material, and that knowledge becomes a permanent part of our technological toolkit. equally transformative would be the leaps in autonomous robotics. The elevator's construction and maintenance require machines that are not just remote-controlled, but truly intelligent. They must perceive a chaotic, unstructured environment, make independent decisions in real time, and execute complex physical tasks like precision welding or delicate repairs with no human in the loop. The artificial intelligence and machine vision systems developed for this would represent a monumental leap forward. These are not algorithms for sorting data or playing games. They are for physical craftsmanship in the void. The same technology could deploy to disaster zones on Earth, where robots could navigate collapsed structures, assess damage, and perform urgent stabilization work long before it is safe for human responders to enter. It could enable deep-sea construction or maintenance of offshore wind farms, operating in equally hostile and remote environments. The elevator teaches machines to be not just tools, but skilled, adaptable partners. Powering such a vast, permanent infrastructure presents another frontier. The climbers and stations need a reliable, continuous energy source far from Earth. This would drive massive advances in space-based solar power, likely using giant, lightweight mirrors or photovoltaic arrays to collect sunlight and beam it as microwaves or lasers to moving targets across thousands of miles. Perfecting this technology of wireless energy transfer at such scale and precision could unlock a clean energy revolution on Earth. Imagine solar farms in geostationary orbit, unaffected by night or weather, beaming abundant power directly to receiving stations on the ground, providing a constant baseline of clean electricity to grids anywhere on the planet. The elevator does not just need power, it forces us to master the art of collecting and transmitting it across the solar system. Finally, the very act of building it would teach us how to construct in space. We would develop entirely new techniques for orbital assembly, robotic coordination, and quality assurance in a vacuum. We would learn to use local resources, turning lunar dust into building materials, a practice known as in situ resource utilization. These construction codes and methods become the foundation for everything that comes next, a how-to manual for building off-world. The first Martian habitats, the large space telescopes at Lagrange points, the interstellar probe assembly yards, all would be built faster and cheaper using the hard-won knowledge from raising the lunar elevator. This project, therefore, is far more than a single bridge. It is a forcing function, a grand challenge that pulls entire fields of science and engineering forward by sheer necessity. The elevator is not the end of a journey, it is the beginning of a new industrial age, both in the heavens and here at home. Yet for all its promise, this grand vision is not without its skeptics. A compelling counter-argument asks a blunt and necessary question: is this magnificent bridge even needed at all? Could we achieve the same goal of cheap, reliable lunar transport with something far simpler? The most prominent alternative is not a bridge but a cannon. Imagine a mass driver, an electromagnetic rail system laid across the lunar surface. Using powerful magnetic pulses, it would accelerate a cargo capsule along its length, hurling it off the end of the track and directly into a low lunar orbit, all without a single drop of rocket fuel. The concept is mechanically elegant, using the moon's lack of atmosphere and low gravity to its full advantage. A mass driver could potentially launch payloads every few minutes, creating a steady stream of material into space. Its components are based on existing electromagnetic technology, and it would be fixed to the ground, avoiding the complexities of a dangling, tens of thousands of miles long cable. On paper, it is a formidable competitor, offering high throughput with seemingly simpler engineering. The challenge, however, lies in the brutal physics of launch. To reach orbit, an object must not only go up, but must also achieve tremendous horizontal speed. A mass driver must impart all that velocity in one violent, instantaneous jolt at the moment of launch. The G-forces involved would be catastrophic for any delicate equipment or potential future passengers, limiting its use to rugged, bulk cargo like containers of water ice or metal ingots. Furthermore, the cargo capsule becomes a high-speed projectile. Precise orbital insertion requires incredibly accurate timing and guidance, a difficult feat for a simple sled. Any error could send the payload crashing back to the surface or tumbling into a useless trajectory. Then there is the issue of the track itself. To achieve orbital velocity, it would need to be dozens of miles long, a massive construction project in its own right, requiring a perfectly flat and stable landscape. While it solves the fuel problem, it introduces new hurdles of precision and acceleration limits. The other major alternative is an evolution of what we already use, the reusable lunar lander, but perfected for a cargo-only role. Companies like SpaceX are demonstrating the power of reusable rocketry with Starship. A dedicated, point-to-point lunar shuttle could, in theory, become so reliable and frequently flown that the cost per kilogram to orbit drops significantly through sheer volume and operational efficiency. This approach leverages technology we are actively developing, avoiding the leap into entirely new systems like space tethers. It offers flexibility, able to land anywhere on the moon and take off from anywhere, not just a fixed equatorial anchor point. The path is familiar, a straight-line improvement on current methods, but this path carries its own baggage, literally. Every flight requires propellant. That propellant must either be manufactured on the moon, which itself requires massive infrastructure, or shipped from Earth at great expense, undermining the goal of cost reduction. Each landing kicks up devastating plumes of abrasive lunar dust, scouring the vehicle and the surrounding area, a major operational headache. And while reuse brings costs down, the fundamental energy equation of rocketry remains, fighting gravity with explosive reaction mass, an inherently less efficient process than a steady electric climb. So where does this leave the space elevator? The debate reveals that no solution is perfect. The mass driver excels at throwing simple bulk goods but fails at delicate delivery. Reusable rockets offer flexibility but remain tied to the physics of fuel. The space elevator, by contrast, is the specialist. It is slow, methodical, and inflexible in its location, but it operates with serene efficiency, turning the immense energy of sunlight into a gentle, continuous flow of cargo of any type. It is not necessarily the only way, but it may be the most optimal way for the specific task of establishing a permanent, high-volume logistics chain between a fixed lunar resource base and a fixed orbital hub. The question shifts from which technology is possible to which one best serves the economy we intend to build. Is the future a landscape of scattered launch pads and hurled cargo, or a single, silent ribbon conducting the heartbeat of a new world? This silent ribbon, for all its promise, would operate under immense and unforgiving tension. A sober assessment of what could go wrong is not pessimism. It is the foundation of responsible engineering. The most dramatic failure mode is a complete cable snap. Picture the tether under constant strain suddenly parting. The immediate result is a violent whiplash effect. The section anchored to the moon would recoil downward, potentially crashing across the surface and destroying the base below. The much longer section extending into space, now suddenly free, would whip outward in a chaotic, unpredictable arc. This isn't just a broken cable. It's the creation of an immense, tangled debris field spanning thousands of miles of Cis-Lunar space. Each fragment, from large counterweight pieces to shredded strands of carbon composite, becomes a high-velocity projectile in delicate lunar orbits, threatening satellites, orbital stations, and future missions for decades. The cleanup would be nearly impossible, potentially rendering key orbital pathways hazardous. A climber malfunction presents a different kind of crisis. A vehicle laden with precious cargo, perhaps volatile fuel or sensitive instruments, could become stranded partway up the cable. It would be stuck, dangling in the void, unable to ascend or descend. Rescuing it would require a complex and dangerous robotic mission to either repair it in place or carefully detach it, all while managing its mass and preserving the tether's integrity. If the cargo were time-sensitive or critical for a deep space mission, this single point of failure could cascade into a logistical nightmare, stranding crews or delaying pivotal launches. Even the seemingly solid ground anchor is a potential vulnerability. Seismic activity, though rare on the Moon, or a direct impact from a larger meteoroid near the base could compromise the foundation. If the anchor shifts or fails, the entire geometric balance of the system is disrupted, putting asymmetric stress on the tether that could lead to a progressive failure. These are not minor glitches, they are scenarios with system-wide consequences. This is precisely why risk mitigation would be the central, non-negotiable design principle from the very first blueprint. The tether would not be a single strand, but a braided bundle of hundreds of independent fibers, so that the failure of a few does not compromise the whole. Multiple, independent power and communication lines would run its length. Climbers would be equipped with backup thrusters and grappling systems to allow for emergency detachment and maneuver. A network of monitoring sensors would constantly measure strain, temperature, and impacts, feeding data to autonomous systems programmed to perform stabilizing adjustments the moment an anomaly is detected. The goal is not to create a system that never fails, but to engineer one that can gracefully degrade, isolate problems, and maintain core functionality even when parts are damaged. It is a philosophy of resilience, building a structure that expects the harsh reality of the space environment and is prepared to endure it. Before we commit to weaving a bridge across the heavens, we must first learn to tie a simple knot in the void. The path to a megastructure begins not with a grand ribbon, but with a humble thread. A crucial, near-term mission could prove the core principles without the staggering cost, a technology demonstrator known as a tethered satellite system. Picture a standard robotic lander touching down on the lunar plains. Its primary mission might be science or resource prospecting, but tucked inside is a secondary payload, a small, boxy subsatellite. After the lander is settled, a mechanism would deploy, unreeling a cable perhaps only a few hundred meters long, connecting the lander on the surface to the subsatellite hovering just above it. This is not a space elevator, but its embryonic cousin, designed to answer the most urgent practical questions. Can we reliably deploy a tether in the lunar vacuum without it tangling or snapping? How does the chosen material react to the brutal temperature swings and relentless dust? Can we control the dynamics of two bodies linked by a thin line in such a weak gravity field? This small-scale test becomes a laboratory in the sky. Engineers would monitor every vibration, every micron of strain on the cable. They would test a simple climber mechanism, a tiny robot that shuttles back and forth on the tether, validating the core propulsion concept. They could even expose sample patches of advanced materials to the full lunar environment, gathering years of durability data in a single mission. The value is immense to risking. A failure here with a cable the length of a few football fields teaches us lessons that would be catastrophic to learn with a cable the length of a planet. It moves the conversation from whiteboard theory to flight-proven hardware, providing the concrete data needed to secure funding for the next, more ambitious step. This first knot in the cosmos is the essential seed from which the great bridge could one day grow. The lunar elevator's ribbon becomes a silent, steady artery, and with its first operational heartbeat, the entire Cis-Lunar system awakens. This is no longer a distant outpost, but a bustling industrial port. Picture automated mining stations at the South Pole, their drills harvesting water ice under the perpetual twilight. This precious resource is not used locally, but loaded into shielded containers that are ferried to the equatorial elevator base. There, a climber secures the cargo and begins its patient multi-day ascent. Upon reaching the Lagrange point depot, the ice is processed into clear, pure hydrogen and oxygen, the fundamental building blocks of rocket fuel. This depot, stocked by the steady flow from below, becomes the most valuable gas station in the solar system. A Mars transfer vehicle arriving from Earth orbit with empty tanks does not need to carry all its propellant for the return journey. It simply docks at the lunar way station, refuels with locally made fuel, and continues its mission with a fraction of the initial mass. The cost of deep space exploration plummets not by a little but by an order of magnitude. The economics shift from a model of extreme scarcity to one of managed abundance. The elevator enables more than just fuel logistics. Imagine factories in lunar orbit fed by raw metallic oxides extracted from the surface regolith. Using concentrated sunlight, they sinter the dust into massive, intricate components, radiation shields for habitats, or structural trusses for giant space telescopes, all in the perfect vacuum and microgravity of space. These manufactured goods, too large or fragile to ever launch from Earth, are now constructed where they are needed and then shipped onward. The Moon transforms from a destination into the primary workshop and supply hub for everything beyond. Personnel movement changes as well. While climbers are too slow for human passengers, they enable the infrastructure that makes human travel safer and more routine. With reliable fuel and supplies waiting in orbit, the risk profile for crewed missions drops dramatically. Cyclers, spacecraft on permanent orbits between Earth and Mars, become sustainable as they can always resupply at the lunar gateway. This creates a rhythmic, scheduled traffic through Cis-Lunar space, a celestial shipping lane governed not by launch windows alone, but by economic demand. In this future, accessing the asteroid belt or the moons of Jupiter no longer requires a heroic, one-off national effort. It becomes a commercial voyage, departing from a port that humanity built together. The elevator's true product is not the cargo it lifts, but the radical accessibility it grants, turning the inner solar system from an impassable gulf into a connected, navigable sea. The verdict emerges not from a single breakthrough, but from the convergence of physics, economics, and human ambition. A lunar space elevator is not only feasible, it is arguably the most pragmatic megastructure humanity could build beyond Earth. The analysis reveals a clear hierarchy of possibility. An Earth-based elevator remains trapped by impossible material demands and a hazardous environment, a dream for a distant future. The lunar version, however, operates within the realm of known physics and foreseeable engineering. Its challenges are monumental, but they are challenges of scale, coordination, and sustained investment, not violations of fundamental law. The material strength required, while still pushing our limits, is within the projected capabilities of next-generation composites. The gravitational balance at the Lagrange points provides a stable anchor that nature itself maintains. The absence of atmosphere and weather removes entire categories of risk that would doom an Earth counterpart. This shifts the conversation from pure speculation to strategic planning. The greatest obstacles are no longer in the stars but here on the ground. They are the human hurdles of international diplomacy, long-term funding, and the collective will to see a century-long project through to completion. This makes the lunar elevator's construction not a question of if, but of when. Its feasibility is proven in theory, waiting only for our civilization to match its technical potential with an equal measure of patience and cooperation. The bridge to the stars is drawn in the blueprint of gravity itself, a silent invitation written across the lunar sky. It asks whether we possess the ingenuity not just to design it, but the perseverance to build it together, forging a new chapter where the moon becomes the first stepping stone in our journey outward. What role do you see humanity playing in that story? Share your thoughts on this celestial ambition below.